Hello there, and welcome to the Sleepless Scientist. Tonight, we turn our gaze upward to the ever-changing canvas above us, the weather. It's something we experience every day, yet rarely pause to truly understand. The breath of wind on your face, the gathering of clouds, the first drop of rain, all of these are stories written in the atmosphere. Tonight, we'll explore how weather is born from sunlight and moisture, how storms gather their power, and how the invisible dance of air shapes everything from gentle breezes to roaring hurricanes. We'll journey through clouds and winds, through seasons and cycles, discovering the patterns that govern the sky above us. So settle in, let the rhythm of rain and wind carry you gently into rest. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. The story of Earth's weather begins. Look up at the sky. What you see is not just emptiness between you and space. It's a dynamic ocean of air, constantly moving, changing, reshaping itself hour by hour. Weather is the state of this atmosphere at any given moment. The temperature, the wind, the humidity, the clouds. It's the breath of the planet. Weather has shaped civilizations. It has decided the outcomes of wars and the fates of harvests. Farmers have watched the sky for millennia, reading the signs. Sailors have learned to respect the wind and storms. Every culture has stories about weather, gods of thunder, spirits of rain, winds that carry souls. The story of Earth's weather begins with the sun. Without the sun's energy, our atmosphere would be still and frozen. But the sun heats different parts of Earth unevenly. The equator receives more energy than the poles. This imbalance creates movement. Heat rises, cold air sinks, and in that movement, weather is born. Tonight we'll trace this story from its beginning. We'll follow the path of energy as it moves through the atmosphere. We'll discover how simple principles, heat, moisture, pressure, combine to create the infinite variety of weather we experience. The atmosphere that surrounds us. The atmosphere is a thin shell of gases wrapped around the Earth. If Earth were an apple, the atmosphere would be thinner than the skin. Yet this fragile layer makes life possible. It shields us from harmful radiation. It holds the oxygen we breathe. It keeps heat from escaping into space. The atmosphere is mostly nitrogen, about 78%. Oxygen makes up 21%. The remaining 1% includes argon, carbon dioxide, water vapor, and trace gases. That 1% matters more than you might think. Water vapor drives weather. Carbon dioxide traps heat. Without these gases, Earth would be a frozen wasteland. The atmosphere has weight. The air pressing down on you right now exerts about 14 pounds per square inch at sea level. You don't feel it because the pressure inside your body balances it. But this pressure is crucial. It determines how air moves, how weather forms, how storms develop. The atmosphere is not uniform. It's thicker at sea level and thins rapidly as you climb. At the peak of Mount Everest, the air is so thin that humans struggle to breathe. Just a few miles higher, there's almost no air at all. The atmosphere that surrounds us is everything. It's the stage on which weather performs. The layers of air above the Earth. The atmosphere is divided into layers, each with distinct characteristics. Starting at the surface, the first layer is the troposphere. This is where we live, and where all weather occurs. It extends from the ground to about 10 kilometers at the poles and up to 18 kilometers at the equator. Temperature decreases with altitude in the troposphere. The higher you go, the colder it gets. Above the troposphere lies the stratosphere, extending to about 50 kilometers. Here, temperature increases with altitude. The ozone layer resides here, absorbing ultraviolet radiation. Airplanes often fly in the lower stratosphere to avoid weather. Beyond the stratosphere comes the mesosphere, reaching 85 kilometers. This is where meteors burn up. Then the thermosphere, where temperatures soar to over 1,000 degrees Celsius, though the air is so thin you wouldn't feel the heat. Finally, the exosphere, where the atmosphere gradually fades into space. Each layer plays a role, but for weather, the troposphere is everything. This is where clouds form, where winds blow, where storms rage. The troposphere is dynamic, turbulent, alive. The layers above are calm and still by comparison. When we talk about weather, we're really talking about the troposphere, the restless, ever-changing bottom layer of air. How weather is born. Weather begins with energy. The sun radiates energy across space. Earth intercepts a tiny fraction of it. This energy heats the surface, land, water, ice. But the heating is uneven. The equator receives more direct sunlight than the poles. Tropical regions are hot. Polar regions are cold. This temperature difference creates imbalance, and nature abhors imbalance. The atmosphere tries to equalize the temperature by moving heat from hot regions to cold ones. Warm air rises, cold air sinks, winds blow, currents circulate. This movement is weather, but it's not just about temperature. Moisture plays a crucial role. Water evaporates from oceans, lakes, rivers. It rises into the air as invisible vapor. When the vapor cools, it condenses into clouds. When clouds grow heavy, they release rain or snow. Pressure also matters. Air has weight. High-pressure areas have sinking air and clear skies. Low-pressure areas have rising air and clouds. The interaction of temperature, moisture, and pressure creates endless variety. A gentle breeze, a torrential downpour, a howling blizzard. All of these are expressions of the atmosphere seeking balance. Weather is born from imbalance, and because the sun never stops shining unevenly, weather never stops changing. The power of the sun. The sun is the engine that drives all weather. Every gust of wind, every raindrop, every storm, all trace their energy back to the sun. The sun's radiation travels through space at the speed of light. In just over 8 minutes, it reaches Earth. Some of this energy reflects off clouds and ice, but much of it is absorbed by the surface. Land and water heat up. The ground warms the air above it. Oceans store enormous amounts of heat. Water has high heat capacity, meaning it takes a lot of energy to change its temperature. This is why coastal areas have milder climates than inland areas. The ocean moderates temperature. Different surfaces absorb heat differently. Dark forests absorb more than reflective snow. Dry deserts heat up quickly and cool down just as fast. Moist soil retains heat longer. These differences create local variations in temperature. And where there are temperature differences, air moves. The power of the sun is constant. It shines on the equator year-round. But at higher latitudes, the sun's angle changes with the seasons. Summer brings long days and direct sunlight. Winter brings short days and slanting rays. This seasonal change drives the yearly cycle of weather. Without the sun, Earth would be a lifeless ice ball. The sun gives energy, and weather is how that energy moves. The movement of heat around the globe. Heat doesn't stay where it's created, it spreads. The equator receives far more solar energy than the poles. If heat stayed put, the tropics would be unbearably hot, and the poles even colder. But the atmosphere and oceans distribute heat around the globe. Warm air rises at the equator, creating a zone of low pressure. This rising air moves toward the poles at high altitude. As it cools, it sinks at about 30 degrees latitude, creating high-pressure zones. This creates circulation cells called Hadley cells. There are other circulation patterns too. Ferrel cells and polar cells. Together, they form a global system of heat transport. Ocean currents also move heat. The Gulf Stream carries warm water from the tropics to the North Atlantic, warming Europe. The Kuroshio Current does the same in the Pacific. Without these currents, London would have the climate of Labrador. The movement of heat around the globe creates climate zones. Tropical zones are hot and wet. Temperate zones have seasons. Polar zones are cold year-round. Weather is the day-to-day variation within these zones. A cold snap in Florida, a heat wave in Norway. Weather is local, but its patterns are shaped by the global movement of heat. How air rises and falls. Air moves vertically, as well as horizontally. Understanding this vertical motion is key to understanding weather. Warm air is less dense than cold air. When air near the ground heats up, it expands and becomes lighter. It rises. As it rises, it moves into regions of lower pressure. The lower pressure allows it to expand further, and expansion causes cooling. This is called adiabatic cooling. It's not that the air loses heat to its surroundings. It cools because it's doing work by expanding. If the rising air cools enough, the water vapor it contains condenses into droplets. A cloud forms. If the air continues to rise, the cloud grows. Rain may follow. Cold air, on the other hand, is dense. It sinks. Sinking air compresses and warms. This is adiabatic warming. As the air warms, any clouds evaporate. The sky clears. This is why high-pressure systems are associated with good weather. The sinking air suppresses cloud formation. How air rises and falls determines what we see in the sky. Rising air creates clouds and storms. Sinking air creates clear, calm conditions. The vertical movement of air is invisible, but its effects are written across the sky every day. The creation of wind. Wind is simply air moving from one place to another. But why does air move? The answer is pressure differences. Air flows from high pressure to low pressure. Imagine two areas side by side. One is cold, with sinking air and high pressure. The other is warm, with rising air and low pressure. Air from the high pressure area flows toward the low pressure area. This flow is wind. The greater the pressure difference, the stronger the wind. But wind doesn't flow in a straight line. Earth's rotation causes moving air to curve. This is the Coriolis effect. In the northern hemisphere, winds curve to the right. In the southern hemisphere, they curve to the left. This curvature creates rotating weather systems, cyclones and anticyclones. Wind has many names around the world. The Mistral in France, the Chinook in North America, the Sirocco in the Mediterranean. Each has its own character. Some winds are hot and dry. Others are cold and damp. Wind shapes the landscape. It erodes mountains, carries sand across deserts, and spreads seeds across continents. It has powered ships for millennia, and now turns turbines to generate electricity. The creation of wind is the atmosphere's way of balancing pressure, and in that balancing act, the air comes alive. The invisible rivers in the sky, high above the ground, rivers of air, flow through the atmosphere. These are jet streams, narrow bands of fast-moving wind at altitudes of 8 to 12 kilometers. Jet streams form at the boundaries between warm and cold air masses. They can reach speeds of over 300 kilometers per hour. Airplanes use jet streams to save fuel and time. Flying east with the jet stream, a plane can shave hours off a transatlantic flight. Flying west against it takes longer. There are two main jet streams in each hemisphere, the polar jet and the subtropical jet. The polar jet meanders, shifting north and south. Its position influences weather patterns. When it dips south, cold Arctic air follows. When it retreats north, warm air moves in. Recently, scientists have discovered atmospheric rivers, narrow corridors of concentrated water vapor. These rivers in the sky transport moisture from the tropics to higher latitudes. When an atmospheric river makes landfall, it can dump enormous amounts of rain, causing floods. The invisible rivers in the sky connect distant parts of the planet. They carry heat, moisture, and energy across continents and oceans. You can't see them, but their effects are felt in every weather forecast. They're the highways of the atmosphere. The role of moisture in the air. Water is essential to weather. The atmosphere is a giant water transport system. Water evaporates from the surface. Oceans, lakes, rivers, soil, plants, and enters the air as vapor. This vapor is invisible. The air can hold only so much moisture. Warm air holds more than cold air. The amount of moisture in the air is called humidity. Relative humidity is the percentage of moisture the air contains compared to the maximum it could hold at that temperature. When air reaches 100% humidity, it's saturated. Any additional moisture condenses into liquid. This is why dew forms on cool mornings. The air cools overnight. Its capacity to hold moisture decreases. Excess moisture condenses onto surfaces. Moisture in the air is potential weather. Dry air is stable. It resists rising. Moisture is unstable. When it rises and cools, clouds form. If enough moisture is present, storms can develop. Hurricanes and thunderstorms are both fueled by moisture. Warm, moist air rises rapidly, releasing heat as water vapor condenses. This heat adds energy to the storm, making it stronger. The role of moisture in the air cannot be overstated. Without it, there would be no clouds, no rain, no snow. Earth would be a barren desert. Moisture is the ingredient that makes weather dynamic and life-sustaining. The birth of a cloud. A cloud is born when air rises and cools. As we've learned, warm air holds more moisture than cold air. When moist air rises over a mountain, in a convection current, or along a weather front, it expands and cools. Eventually, it reaches a temperature where it can no longer hold all its moisture. This temperature is called the dew point. When the dew point is reached, water vapor condenses into tiny droplets. These droplets are microscopic, suspended in the air by updrafts. Billions of them together form a visible cloud. But condensation needs a surface to occur. In the atmosphere, this surface is provided by aerosols, tiny particles of dust, salt, pollen, or pollution. Water vapor condenses onto these particles, forming cloud droplets. Without aerosols, clouds would struggle to form. The birth of a cloud is a visible marker of atmospheric processes. It tells us that air is rising, that moisture is present, that conditions are changing. Different clouds form under different conditions. Some clouds are thin and wispy, others are towering and dark. The shape and type of cloud reveal what's happening in the atmosphere. Clouds are not just beautiful, they're messengers, telling stories written in condensed moisture and rising air. The different shapes of clouds. Clouds come in many forms, each with its own name and character. Meteorologists classify clouds by altitude and appearance. At high altitudes, above 6 kilometers, we find cirrus clouds. These are thin, wispy, made of ice crystals. They often appear in fair weather, but can signal an approaching storm. At mid-altitudes, 2 to 6 kilometers, there are altostratus and altocumulus clouds. Altostratus clouds form gray or blue sheets that cover the sky. Altocumulus clouds appear as puffy, layered patches. At low altitudes, below 2 kilometers, we find stratus, stratocumulus and nimbostratus clouds. Stratus clouds form low gray layers. Stratocumulus are lumpy and patchy. Nimbostratus are thick, dark rain clouds. Then there are clouds with vertical development, cumulus and cumulonimbus. Cumulus clouds are the fluffy, fair weather clouds you see on summer days. Cumulonimbus are towering storm clouds that can reach the stratosphere. Each cloud type forms under specific conditions. Cirrus clouds form in stable, high-altitude air. Cumulonimbus form in unstable air with strong updrafts. By observing clouds, you can predict the weather. Cirrus clouds may precede a warm front. Dark nimbostratus mean rain is imminent. The different shapes of clouds are a visual language. Learn to read them, and the sky will speak to you. The gentle drift of cirrus clouds. Cirrus clouds are among the highest and most delicate. They form at altitudes above 6 kilometers, where temperatures are well below freezing. Cirrus clouds are made entirely of ice crystals. These crystals are small and light, caught in the wind, drifting slowly across the sky. Cirrus clouds appear as thin, wispy streaks, mare's tails, they're sometimes called. They're often the first sign of an approaching warm front. As the front approaches, the cirrus clouds thicken into cirrostratus, then lower and become altostratus. Rain may follow within a day or two. Despite their association with changing weather, cirrus clouds themselves are benign. They don't produce precipitation. They're too high and too thin. Sunlight passes through them, sometimes creating halos around the sun or moon. These halos are caused by light refracting through the ice crystals. Cirrus clouds are beautiful. They catch the colors of sunrise and sunset, glowing pink and orange, long after lower clouds have gone dark. They're the last to light up in the evening, and the first to glow in the morning. The gentle drift of cirrus clouds is a reminder of the constant motion in the atmosphere. Even at great heights, air flows, clouds form, drift, and dissipate. The sky is never still. The heavy weight of cumulonimbus. Cumulonimbus clouds are the giants of the atmosphere. They tower from near the ground to the edge of the stratosphere, sometimes reaching heights of 15 kilometers or more. These are the storm clouds. Dark, ominous, filled with energy. Cumulonimbus clouds form in unstable air. Warm, moist air rises rapidly. As it rises, it cools and condenses. Latent heat is released, warming the air and making it rise even faster. This creates powerful updrafts. The cloud grows vertically, piling higher and higher. The top of a cumulonimbus often spreads out into an anvil shape. This happens when the rising air reaches the tropopause, the boundary between the troposphere and stratosphere. It can't rise further, so it spreads horizontally. Inside a cumulonimbus, conditions are violent. Updrafts and downdrafts churn. Ice particles and water droplets collide. Lightning sparks. Rain falls in torrents. Sometimes hail forms. Cumulonimbus clouds produce thunderstorms, heavy rain, lightning, hail, and sometimes tornadoes. They can drop inches of rain in minutes. They're dangerous and awe-inspiring. The heavy weight of cumulonimbus clouds is both literal and metaphorical. They're filled with water and ice, tons of it suspended in the air, and they carry the weight of the storm, power, and destruction. Respect them, admire them from a distance. When clouds begin to rain, a cloud can hold only so much moisture. As droplets collide and merge, they grow larger. When they become too heavy to be supported by updrafts, they fall. This is rain, but the process is more complex than it seems. In warm clouds, where temperatures are above freezing, rain forms through collision and coalescence. Tiny droplets bump into each other, sticking together. As they merge, they grow. A typical raindrop is about 1,000,000 times larger than a cloud droplet. In cold clouds, where temperatures are below freezing, ice crystals form. These crystals grow by collecting supercooled water droplets. The droplets freeze onto the crystal, making it larger. Eventually, the crystal falls and melts into a raindrop. Sometimes ice crystals don't melt. They reach the ground as snow. Sometimes, they partially melt and refreeze, becoming sleet. When clouds begin to rain, they're releasing the moisture they collected from evaporation. Rain returns water to the surface, completing part of the water cycle. Rain nourishes the land. It fills rivers and lakes. It sustains forests and crops. Without rain, life would be impossible in most regions. Rain also cleanses the air, washing out dust and pollutants. After a storm, the air smells fresh. The world feels renewed. When clouds begin to rain, they're giving back what they took. It's a gift from the sky. The formation of raindrops. Raindrops are not teardrop-shaped as often depicted. Small raindrops are nearly spherical. Larger ones flatten on the bottom due to air resistance, becoming more like hamburger buns. Very large raindrops break apart. A raindrop forms when cloud droplets collide and merge. But cloud droplets are tiny. about 10 to 20 micrometers in diameter. A raindrop is about 2 millimeters, 100 times larger. How do droplets grow so large? Through collision and coalescence. Larger droplets fall faster than smaller ones. As they fall, they sweep up smaller droplets in their path. Each collision adds to the droplet size. In clouds with strong updrafts, droplets can be carried upward repeatedly, colliding with more droplets each time. They grow larger with each cycle. Eventually, they become too heavy to be lifted. They fall as rain. In cold clouds, ice crystals play a role. The Bergeron process describes how ice crystals grow at the expense of supercooled water droplets. Ice has a lower vapor pressure than liquid water. Water vapor preferentially deposits onto ice crystals, making them grow. The formation of raindrops is a delicate balance of physics. Temperature, updrafts, droplet size, and time all matter. But the result is simple: rain. The drops that fall from the sky and soak the earth. The sound of falling rain. Rain has a sound. It's one of nature's most soothing rhythms. A gentle patter on a roof, a steady drumming on pavement, a soft hiss as it falls through leaves. The sound varies with intensity. Light rain, whispers, heavy rain roars. The surface matters too. Rain on metal creates a sharp, clear sound. Rain on grass is muted and soft. Rain on water produces gentle plops. The sound of falling rain has been recorded, studied, and cherished. Many people find it calming. It's used in meditation and sleep aids. There's something primal about it, a reminder of nature's cycles. Rain is sound made from water and gravity. Each drop is a tiny percussion instrument. Billions of them together create a symphony. Thunder may accompany rain. Wind may drive it sideways. But even in a storm, the sound of rain persists beneath the chaos. Steady, relentless, cleansing. Rain speaks to us. It tells us to slow down, to stay inside, to rest. The sound of falling rain is a lullaby from the sky. Let it wash over you. Let it carry your thoughts away. Rain has been falling for billions of years. It will fall long after we're gone. It's eternal. It's patient. It's peaceful. The life cycle of a storm. A storm is born, grows, and dies. This cycle can take hours or days. It begins with instability. Warm, moist air rises. If conditions are right, strong updrafts, plenty of moisture, instability in the atmosphere. A storm cell forms. The developing stage is marked by strong updrafts. A cumulus cloud grows rapidly, piling higher. Water vapor condenses, releasing latent heat. The heat warms the air, making it rise faster. The cloud grows into a towering cumulonimbus. In the mature stage, the storm reaches its peak. Updrafts and downdrafts coexist. Rain falls heavily. Lightning flashes. Thunder rumbles. The storm is most intense now. It may produce hail, strong winds, even tornadoes. The dissipating stage begins when downdrafts dominate. Cool air from the downdrafts cuts off the warm air supply. Without warm air to fuel it, the storm weakens. So rain becomes lighter. The clouds spread out and thin. Eventually, the storm dies. What remains is stratocumulus clouds and clearing skies. The life cycle of a storm is a reminder of impermanence. Even the most powerful storm is temporary. It builds, rages, and fades. The sky calms. The sun returns. The storm becomes a memory. The calm before the rain. There's a moment before a storm when everything changes. The air grows still. The wind stops. Birds fall silent. The sky darkens. This is the calm before the rain. It's a brief pause, a held breath before the storm arrives. Scientifically, this calm occurs because of changes in pressure and wind patterns. As a storm approaches, the winds shift. A temporary lull can occur between the outflow of one system and the inflow of another. Psychologically, the calm feels ominous. We sense the approaching storm. The air feels heavy, charged with electricity. Humidity rises. The temperature may drop slightly. There's a tension in the atmosphere. Humans have felt this for millennia. We've learned to read the signs: darkening clouds, the smell of rain, the stillness. Animals sense it too. Cattle lie down. Birds seek shelter. Then the calm breaks. The first drops fall. The wind picks up. The storm arrives. But for a moment, before the rain, there's peace. It's a reminder that change is coming, that the world is about to shift. The calm before the rain is nature's way of preparing us. It's a gift, a moment to find shelter, to brace ourselves, and then the storm begins. Thunder and lightning. Lightning is one of nature's most dramatic phenomena. It's a massive electrical discharge between a cloud and the ground, or between clouds. Thunder is the sound that discharge creates. Lightning begins with charge separation in a storm cloud. Ice particles and water droplets collide. Friction strips. Electrons. Positive charges accumulate in the upper part of the cloud. Negative charges gather in the lower part. The ground below becomes positively charged. When the charge difference becomes large enough, it overcomes air's resistance. A channel of ionized air forms, a stepped leader descending from the cloud. When it nears the ground, a streamer of positive charge rises to meet it. They connect. Electrons rush down the channel. This is the return stroke. The bright flash we see is lightning. The channel heats to about 30,000 degrees Celsius, 5 times hotter than the sun's surface. This intense heat causes the surrounding air to expand explosively. The expansion creates a shock wave. Thunder. Thunder and lightning are inseparable. Light travels much faster than sound. We see the flash almost instantly. Sound takes about 3 seconds to travel 1 kilometer. Count the seconds between lightning and thunder. Divide by 3, and you know how far away the storm is. Thunder and lightning are reminders of the atmosphere's power. Electricity in the sky, sound from superheated air, nature's most spectacular show. What really causes a lightning strike? Lightning is electricity. But what causes it? Inside a storm cloud, particles collide. Updrafts carry small ice crystals upward. Larger hail and grape fall. These collisions transfer charge. The mechanism isn't fully understood, but the result is clear. The upper part of the cloud becomes positively charged. The lower part becomes negative. The ground beneath the cloud becomes positively charged through induction. Negative charges in the ground are repelled downward. Positive charges accumulate at the surface. The stage is set. When the electric field becomes strong enough, about 3 million volts per meter, air breaks down. It ionizes, becoming conductive. A stepped leader descends from the cloud in discrete steps, branching as it seeks the path of least resistance. When it nears the ground, positive streamers rise from tall objects, trees, buildings, towers. The leader and streamer connect. A conductive path is complete. This is the return stroke, the brilliant flash we see. Multiple strokes can follow the same channel in rapid succession, creating a flickering effect. What really causes a lightning strike is the buildup of electrical potential and the breakdown of air's resistance. It's a natural capacitor discharging. It's physics made visible, and it's beautiful and terrifying in equal measure. The sound that follows light. Thunder is the voice of lightning. It's the sound created when lightning heats the air to extreme temperatures. The air expands faster than the speed of sound, creating a shock wave. This shock wave is thunder. Thunder is not just one sound. It's a complex mix of frequencies. The initial crack is the shock wave from the nearby part of the lightning channel. The rumble that follows is sound from distant parts of the channel, reaching you at different times. Thunder can be sharp and sudden if lightning is close. It can be a long rolling rumble if lightning is far away, or if the lightning channel is long and horizontal. Mountains and buildings reflect thunder, creating echoes and extending the sound. Thunder travels about 1 kilometer in 3 seconds. By counting the seconds between lightning and thunder, You can estimate distance. If you see lightning and hear thunder instantly, the strike was very close. Seek shelter immediately. The sound that follows light is a reminder of nature's power. It's loud, rumbling, sometimes frightening, but it's also beautiful. Thunder tells us that the storm is alive. It's moving, it's releasing energy, and somewhere in that sound is the raw, untamed voice of the atmosphere. The fragrance of earth after rain. Rain has a smell. It's earthy, fresh, almost sweet. This scent is called petrichor, from the Greek words for stone and the fluid that flows in the veins of gods. Petrichor is created by several compounds. One is geosmin, produced by soil bacteria called actinomycetes. These bacteria thrive in moist soil. During dry periods, they produce geosmin. When rain falls, the water releases geosmin into the air. Humans are extremely sensitive to geosmin. We can detect it at concentrations as low as 5 parts per trillion. It's one of the most recognizable smells in nature. Another contributor is plant oils. During dry weather, plants release oils that accumulate on rocks and soil. Rain releases these oils into the air, adding to the scent. Ozone also plays a role. Lightning splits oxygen molecules in the air, creating ozone. Ozone has a sharp, clean smell. It's carried by downdrafts to the ground. Together, geosmin, plant oils, and ozone create the fragrance of earth after rain. It's a smell of renewal, of life returning, of the earth drinking deeply after a long thirst. The fragrance of earth after rain is a gift. It reminds us that rain nourishes, that water is life, that the world is fresh and clean after a storm. The making of a rainbow. A rainbow is sunlight made visible through water. It's one of nature's most beautiful phenomena. Rainbows form when sunlight interacts with raindrops. Sunlight is white light, composed of all colors. When light enters a raindrop, it slows and bends, refracts. Different colors bend by different amounts. Red bends least, violet bends most. Inside the drop, light reflects off the back surface. Then it exits the drop, bending again. The result is that white light separates into a spectrum of colors. Each raindrop produces a full spectrum, but you only see one color from each drop, depending on the angle between the sun, the drop, and your eye. The angle for red light is about 42 degrees. For violet, about 40 degrees. Millions of raindrops, at different angles, produce the arc of colors we see as a rainbow. To see a rainbow, the sun must be behind you, and rain must be in front of you. The lower the sun, the higher the rainbow. Sometimes, you see a double rainbow. The second, fainter arc is caused by light reflecting twice inside the drops. The colors are reversed, violet on top, red on bottom. The making of a rainbow is pure physics. Refraction, reflection, dispersion. But the result is magical. A rainbow is light and water dancing together. It's a promise that the storm has passed. The colors hidden in the sky. The sky is full of colors we don't always notice. At noon, it's blue. At sunset, it's orange and red. At twilight, it's purple and pink. These colors come from sunlight scattering in the atmosphere. Sunlight is white light, a mix of all colors. When it enters the atmosphere, it collides with gas molecules. These collisions scatter the light. Blue and violet light have shorter wavelengths. They scatter more easily than red and orange. During the day, the sky appears blue because we see the scattered blue light from all directions. At sunset, the sun is low. Its light travels through more atmosphere. Most of the blue scatters away before reaching your eyes. What remains is red and orange. The sky glows warm. After sunset, the sky doesn't go dark immediately. Sunlight still illuminates the upper atmosphere. This creates twilight, a time of soft, diffuse light. The sky may turn pink, purple, or deep blue. These colors are caused by scattering at different altitudes. The colors hidden in the sky are a reminder that light and air interact in beautiful ways. The sky is not just a blank canvas, it's a living display of physics. Every moment, the colors change. Pay attention. The sky is always speaking in color, the dance of sunlight and water. Sunlight and water create much of the beauty in weather. Rainbows, halos, sundogs. These optical phenomena result from light interacting with water droplets or ice crystals. Halos form around the sun or moon when light passes through ice crystals and cirrus clouds. The crystals act like prisms, bending light. A circular halo appears at a 22-degree radius. Sundogs, or perhelia, are bright spots on either side of the sun. They form when sunlight refracts through hexagonal ice crystals falling with their faces horizontal. Sundogs are often colorful, with red nearest the sun. Glories are colorful rings around the shadow of your head when you're above a cloud or fog. They're caused by light diffracting around water droplets. Pilots and mountain climbers often see glories. Coronas are colored rings around the sun or moon, smaller than halos. They form when light diffracts through small, uniform water droplets. The dance of sunlight and water is endlessly creative. Each phenomenon requires specific conditions, specific angles, specific particles. But when conditions align, the sky rewards us with beauty. These displays are fleeting. They last minutes or seconds. If you see one, stop, watch. The sky is performing, and the show won't last forever. The beauty of snowflakes. Snowflakes are ice crystals that form in clouds and fall to the ground. Each one is unique. This uniqueness comes from the conditions the crystal experiences as it forms. Snowflakes begin as tiny ice crystals around a nucleus. A speck of dust or pollen, water vapor in the cloud deposits onto the crystal, making it grow. The shape depends on temperature and humidity. At around -2 degrees Celsius, crystals grow as thin plates. At -5, they grow as needles. At -15, they become plates again. As the crystal tumbles through the cloud, it experiences different temperatures and humidity levels. Each change affects how it grows. The result is an infinitely varied structure. No two snowflakes experience exactly the same path. Under a microscope, snowflakes reveal stunning symmetry. Six-fold symmetry is common because of water's molecular structure. The beauty of snowflakes is mathematical and natural. They're crystals following physical laws. Yet they're also art. Each one is a tiny sculpture made of ice. When millions fall together, they transform the world. The ground becomes white. Sounds are muffled. Everything softens. Snowflakes are fragile. They melt at a touch, but together, they're powerful. They build mountains of snow. They shape landscapes. The beauty of snowflakes reminds us that nature creates art at every scale. Even in something as simple as falling snow. How snow is formed in the clouds. Snow forms when water vapor deposits directly onto ice crystals without becoming liquid first. This process is called deposition. It happens in clouds where temperatures are below freezing. Not all cold clouds produce snow. The cloud must be cold enough and contain enough moisture. Ice crystals form around nuclei, tiny particles suspended in the air. Once formed, the crystals grow as water vapor deposits onto them. The shape of the crystal depends on temperature and humidity as it grows. If the crystal stays cold all the way to the ground, it arrives as snow. If it falls through warm air, it melts into rain. If it melts and refreezes, it becomes sleet. Snow is most common when surface temperatures are at or below freezing. But snow can fall at slightly warmer temperatures if the air is dry enough. The falling snow cools the air around it through a process called evaporative cooling. How snow is formed in the clouds is a delicate process. It requires cold temperatures, moisture, and ice nuclei. But when conditions align, snow transforms the landscape. It blankets the ground. It quiets the world. And for a moment, everything feels still and pure. The silence of falling snow. Snow absorbs sound. When snow falls, the world becomes quieter. This happens because fresh snow has a porous structure. The spaces between snowflakes trap sound waves, preventing them from traveling. Heavy snowfall can reduce sound levels significantly. Conversations become muffled. Traffic noise fades. Even your footsteps sound softer. There's a psychological component too. Snow falling gently from the sky creates a sense of calm. It's slow, peaceful. Watching snow fall is meditative. The silence of falling snow is not absolute. If you listen carefully, you might hear a faint whisper, the sound of snowflakes brushing against each other and landing on surfaces. In heavy snow, you might hear the wind, but overall, snow quiets the world. After a snowfall, the silence continues. Fresh snow on the ground absorbs sound. The world feels insulated, wrapped in a blanket. This changes as the snow ages. As it compacts and melts, it becomes less effective at absorbing sound. But for a time, after a fresh snowfall, there's a deep, profound quiet. The silence of falling snow is a gift. It invites us to slow down, to listen to the quiet, to rest in the stillness. Snow transforms not just the landscape, but the soundscape too. The chill of winter air. Winter air is cold and often dry. When temperatures drop, the air's capacity to hold moisture decreases dramatically. Cold air near freezing holds only a fraction of the moisture that warm summer air holds. This is why winter air often feels dry. It simply can't contain much water vapor. The chill of winter air penetrates. Cold air is denser than warm air. It sinks, settling in valleys and low areas. On clear winter nights, the ground radiates heat into space. The air near the surface cools rapidly. This creates temperature inversions, layers of cold air trapped beneath warmer air above. Frost forms on surfaces. Breath becomes visible. The chill is sharp and biting. Wind makes cold air feel even colder. Wind chill is the perceived decrease in temperature caused by wind, removing heat from exposed skin. A temperature of -10 degrees Celsius feels much colder with a strong wind. The chill of winter air shapes life. Animals grow thick coats or hibernate. Plants go dormant. Humans bundle up, seeking warmth. But winter air is also invigorating. It's crisp, clear, refreshing. It sharpens the senses. The cold reminds us that seasons change, that the earth cycles through cold and warm. Winter air is temporary. Spring will come. But for now, the chill settles in. The frost that paints the morning. Frost is ice that forms on surfaces when water vapor deposits directly from air to solid. It's most common on clear, calm nights when temperatures drop below freezing. The surface grass, car windows, leaves cools by radiating heat into space. If the surface cools below the dew point and below freezing, frost forms. Frost appears as delicate ice crystals. Under magnification, the crystals are beautiful, feathery, intricate, geometric. They grow as water molecules in the air, attached to the surface, building layer by layer. Different types of frost exist. Hoar frost forms thick, feathery crystals on trees and plants. Rime frost forms when supercooled fog droplets freeze onto surfaces. Window frost creates intricate patterns on glass. Frost transforms the world overnight. A landscape that was green yesterday is now white and sparkling. Sunlight catches the crystals, making everything glitter. Frost is temporary. As the sun rises and temperatures climb, the frost melts. Water returns to the air. By midday, the frost is gone, as if it never existed. The frost that paints the morning is nature's artwork. It's ephemeral, beautiful, and free. It reminds us that beauty can appear overnight and disappear just as quickly. Appreciate it while it lasts. The mystery of ice crystals. Ice crystals are water molecules arranged in a hexagonal lattice. This structure is why snowflakes have six-fold symmetry. The hydrogen bonds between water molecules dictate the geometry. Ice crystals can form in clouds, on the ground, or on surfaces. Each formation process creates different structures. In clouds, crystals form from water vapor. On the ground, frost forms through deposition. In freezing rain, liquid water freezes on impact. The mystery of ice crystals lies in their diversity. Though they all follow the same molecular rules, the shapes vary wildly. Temperature, humidity, and time all influence growth. Scientists have studied ice crystals for centuries. Kenneth Liebrecht, a physicist, has created detailed guides to snowflake types. He's grown snowflakes in laboratories, controlling conditions to produce specific shapes. Yet mysteries remain. Why do some crystals grow symmetrically, while others are irregular? How do branches know to grow in coordination? The full physics is complex and not entirely understood. Ice crystals are also beautiful. Under microscopes, they reveal patterns that seem impossibly intricate. Nature, following simple rules, creates complexity. The mystery of ice crystals is a reminder that even common things, water, cold, air, can produce wonders. Look closely. The world is full of hidden marvels. The power of a blizzard. A blizzard is not just heavy snow, it's a combination of snow, wind, and cold. Officially, a blizzard has winds of at least 56 kilometers per hour, visibility below 400 meters, and lasts at least 3 hours. Blizzards are dangerous. The wind drives snow horizontally. Visibility drops to near zero. Whiteout conditions occur. You can't see the ground or the sky. Everything is white. Disorientation is common. People have gotten lost meters from their homes. The cold is intense. Wind chill can drop temperatures to life-threatening levels. Exposed skin can freeze in minutes. The power of a blizzard comes from the combination of elements. Snow alone is manageable. Wind alone is tolerable. But together, they create a hostile environment. Snow drifts pile up, blocking roads and burying vehicles. Power lines snap under the weight of ice and wind. Communities can be isolated for days. Yet blizzards are also awe-inspiring, their nature unleashed. The howling wind, the swirling snow, the raw power is humbling. Blizzards remind us that nature is stronger than we are, that we must respect it, that survival sometimes means staying inside and waiting for the storm to pass. The power of a blizzard is not to be underestimated. The weight of frozen storms. Ice storms occur when rain falls through a layer of freezing air near the ground. The rain doesn't freeze in the air. It remains liquid but supercooled. When it hits surfaces, roads, trees, power lines, it freezes instantly. This creates a coating of ice called glaze. Glaze ice is smooth, clear, and incredibly heavy. A thin layer doesn't seem like much, but ice accumulates. A half-inch coating on a tree branch can add hundreds of pounds of weight. Branches bend and break. Trees crack and fall. Power lines snap under the load. The sound of breaking branches echoes through forests. Ice storms can cause widespread damage. Power outages can last days or weeks. Roads become skating rinks. Walking is treacherous. Yet ice storms create a strange beauty. Trees become encased in glass. Sunlight catches the ice, creating dazzling displays. Every branch, every blade of grass, sparkles. But the beauty comes at a cost. The weight of frozen storms is immense. Recovery is slow. Communities pull together, clearing debris, restoring power, checking on neighbors. Ice storms are reminders of winter's harshness. They're beautiful and destructive in equal measure, and they teach us resilience and preparedness. The melting of spring. Spring arrives gradually. The sun climbs higher. Days lengthen. Temperatures rise. Snow begins to melt. At first, the melting is slow. Snow softens during the day, refreezes at night, but as temperatures remain above freezing, the melt accelerates. Snowpack disappears. Water flows. Streams swell. Rivers rise. The melting of spring releases stored water. Winter snow acts as a reservoir. In mountains, snowmelt feeds rivers throughout summer. Without it, many regions would face drought. Spring melt can cause flooding. If snow melts too quickly, rivers overflow, ice jams can form, blocking water and causing sudden floods when they break. But melting also brings renewal. The ground thaws, seeds germinate, plants push through the soil, trees bud, migrating birds return. Spring is awakening. The melting of spring is a transition. Winter releases its grip. The earth warms. Life returns. It's a cycle as old as the planet. Spring melts the frozen world and prepares it for summer. The melting is messy, mud, slush, dripping eaves. But it's necessary. It's the earth shedding winter's coat, and beneath, life is stirring. The awakening of warm winds. As spring progresses, winds change. Cold Arctic air retreats. Warm air from the tropics moves northward. These warm winds carry moisture and energy. They melt snow. They warm the soil. They signal that winter is ending. In some regions, warm winds have names. The Chinook in North America is a warm, dry wind that descends the eastern slopes of the Rockies. It can raise temperatures by 20 degrees Celsius in hours. Snow melts rapidly, earning it the nickname Snow Eater. In Europe, the Foehn wind has similar effects. These winds are created when air flows over mountains. As air rises, it cools and releases moisture as rain or snow. As it descends the other side, it warms and dries. The result is a warm, dry wind. The awakening of warm winds is a relief after a long winter. People feel energized. The change is invigorating. But warm winds can also cause problems. Rapid snowmelt leads to flooding. Dry conditions increase wildfire risk. Yet overall, warm winds are welcome. They're harbingers of spring. They carry the promise of warmer days. The awakening of warm winds is nature's way of saying winter is over. Summer is coming. The cycle continues. The arrival of summer storms. Summer brings its own weather. Heat builds during the day. The sun warms the ground. The ground heats the air. Warm, moist air rises rapidly. By afternoon, towering cumulus clouds form. These clouds can grow into thunderstorms. Summer storms are common in many regions. They're fueled by heat and moisture. The atmosphere becomes unstable. Convection is strong. Storms develop quickly. Within an hour, a clear sky can become dark and threatening. Summer storms often occur in late afternoon or early evening. The timing reflects the peak heating of the day. The storms are intense, but usually brief. They drop heavy rain, produce lightning, and sometimes hail. Then they pass. The arrival of summer storms is a daily rhythm in tropical and temperate regions. The storms cool the air. They water the land. They're part of the summer pattern, but they can be severe. Flash flooding is a risk. Lightning is dangerous. Strong winds can down trees. Summer storms are powerful reminders that even in warm, pleasant weather, the atmosphere has energy to release. Respect the storms, seek shelter, and marvel at the power of heat and moisture combined. The energy stored in the sky. The atmosphere is a giant battery, storing energy from the sun. This energy drives all weather. Heat is stored in air masses, in water vapor, in rising currents. When conditions are right, the energy releases, sometimes slowly, as steady rain, sometimes explosively, as thunderstorms or tornadoes. The most dramatic releases occur in convective storms. Warm, moist air rises rapidly. As water vapor condenses, latent heat is released. This heat warms the air further, making it rise faster. The storm intensifies. Updrafts can reach speeds of over 100 kilometers per hour. The energy stored in the sky is immense. A single thunderstorm can release energy equivalent to a small nuclear weapon. Hurricanes release even more, the energy of several nuclear bombs per second. Where does this energy come from? Ultimately, the sun. Solar radiation heats the surface. Water evaporates. Warm air rises. The energy is transferred from sunlight into the atmosphere. The energy stored in the sky is invisible until it's released. Then we see lightning, feel the wind, hear the thunder. The release is dramatic, but the storage is gradual, quiet, constant. The sky is always gathering energy, and weather is the release. The birth of a thunderstorm. A thunderstorm begins with heat and moisture. On a summer afternoon, the sun heats the ground. The ground warms the air. If the air is moist, it rises. As it rises, it cools. Water vapor condenses. A cumulus cloud forms. If updrafts are strong and the atmosphere is unstable, the cloud continues to grow. It towers upward, becoming a cumulonimbus. This is the developing stage. Inside the cloud, water droplets and ice particles collide. They grow larger. Updrafts carry them upward repeatedly. Eventually, they become too heavy. They fall as rain. This initiates downdrafts. The storm enters its mature stage. Rain falls heavily. Lightning flashes. Thunder booms. The storm is at its peak. Updrafts and downdrafts coexist. Energy is released. But storms don't last forever. The downdrafts eventually cut off the warm air supply. Without warm, moist air feeding it, the storm weakens. It enters the dissipating stage. Rain lightens. Clouds thin. The storm fades. The birth of a thunderstorm is rapid. From first cloud to peak intensity can take less than an hour. The storm lives fast and dies young. But while it lives, it's spectacular. How tornadoes form. Tornadoes are rotating columns of air that extend from a thunderstorm to the ground. They're among the most violent weather phenomena on Earth. Tornadoes form under specific conditions. You need a strong thunderstorm, wind shear, and instability. Wind shear is a change in wind speed or direction with height. It creates rotation in the air. When this rotation is initially horizontal, but updrafts in a thunderstorm can tilt the rotation vertical. Now you have a rotating updraft, a mesocyclone. Most mesocyclones don't produce tornadoes, but if conditions are right, a funnel cloud descends from the base of the storm. If it touches the ground, it's a tornado. Tornadoes vary in strength. The enhanced Fujita scale rates them from EF0 to EF5. An EF0 tornado has winds under 135 kilometers per hour. An EF5 has winds over 320 kilometers per hour. The strongest tornadoes are devastating. They can destroy entire towns. How tornadoes form is still not fully understood. Scientists use radar and storm chasers to study them. But tornadoes are unpredictable. They can form quickly and dissipate just as fast. Tornadoes are reminders of the atmosphere's raw power. They're beautiful and terrifying, and they command respect. The eye of a twister. Tornadoes don't have eyes the way hurricanes do, but at the center of a tornado's rotation is a core of low pressure. The visible funnel is condensed water vapor and debris. Inside, the air is rotating rapidly. The strongest winds are usually found in the outer part of the funnel, not the center. People who have survived direct hits by tornadoes sometimes report a moment of calm at the center. The winds die. The roar stops briefly. Then the other side of the tornado hits, and the violence resumes. This is not a true eye. It's just the brief moment when the center passes over. Tornadoes are loud. Survivors describe a sound like a freight train or jet engine. The wind roars. Debris crashes. It's overwhelming. The eye of a twister, if it can be called that, offers no real refuge. Tornadoes are too small and fast-moving. The calm lasts seconds. The best strategy is to avoid tornadoes entirely. Seek shelter underground, if possible. Tornadoes are unpredictable. They can change direction suddenly. They can lift and touch down again. The eye of a twister is a myth. There's no safe spot in a tornado, only survival and luck. The destruction and power of wind. Wind is moving air, but when it moves fast, it becomes a force of destruction. Hurricanes, tornadoes, derechos. These windstorms can level buildings, uproot trees, and toss vehicles. The power of wind increases exponentially with speed. A breeze at 20 kilometers per hour is pleasant. A gale at 80 kilometers per hour is challenging to walk against. A hurricane at 200 kilometers per hour is catastrophic. Wind exerts pressure on surfaces. The pressure increases with the square of the wind speed, double the wind speed, and the force quadruples. At high speeds, wind becomes a battering ram. Flying debris becomes deadly. Roofs peel off. Windows shatter. The destruction and power of wind are humbling. We build structures to withstand it, but nature sometimes wins. Tornadoes carve paths through towns. Hurricanes devastate coastlines. Yet wind is also essential. It distributes heat. It mixes the atmosphere. It powers wind turbines and sailing ships. Wind is both creator and destroyer. It shapes landscapes, eroding mountains and building dunes. The destruction and power of wind remind us of our place. We're at the mercy of forces far larger than ourselves. Respect the wind. The beauty and terror of hurricanes. Hurricanes are massive tropical cyclones. They form over warm ocean waters, where heat and moisture provide fuel. A hurricane is a heat engine. Warm, moist air rises. As it rises, it cools and condenses, releasing latent heat. The heat warms the air further, making it rise faster. This creates a low-pressure center. Air spirals inward. The Coriolis effect, from Earth's rotation, gives the storm its characteristic spin. Hurricanes are enormous. They can span hundreds of kilometers. Their winds can exceed 250 kilometers per hour. They produce torrential rain, storm surges, and tornadoes. The beauty of hurricanes is visible from space. They're perfect spirals, white clouds swirling around a clear eye. From above, they're mesmerizing, but on the ground, they're terrifying. The wind howls, rain falls in sheets. The surge floods coastlines. Hurricanes are among the deadliest natural disasters. The beauty and terror of hurricanes are inseparable. They're nature's most powerful storms. They form over weeks, travel thousands of kilometers, and leave devastation in their wake. Yet they're also essential. They transport heat from the tropics to higher latitudes. They're part of Earth's climate system. Hurricanes are forces of nature, beautiful, terrible, awe-inspiring. The calm at the eye of the storm. The eye of a hurricane is a region of calm at the center. Inside the eye, winds are light, skies are often clear or partly cloudy. The sun may shine. It's a stark contrast to the chaos just outside. The eye is created by the storm's structure. Air spirals inward, then rises in the eye wall, a ring of intense thunderstorms surrounding the eye. The eye wall has the strongest winds and heaviest rain. Inside the eye, air slowly sinks. Sinking air warms and dries, suppressing clouds. The eye can be 20 to 60 kilometers across. Ships caught in a hurricane have reported passing through the eye. For a time, conditions are calm. Then the other side of the eye wall hits, and the storm resumes. The calm at the eye of the storm is deceptive. It's not safety. It's a brief respite. The storm is still there, just temporarily absent. People on land sometimes emerge during the eye, thinking the storm is over. This is dangerous. The other side will arrive soon. The eye is a reminder that storms have structure. They're not just chaos. They're organized, rotating systems. And at the center of the chaos, there's a moment of calm. It's eerie, beautiful, and temporary. The ocean's influence on storms. The ocean plays a crucial role in weather. It covers 71% of Earth's surface. It absorbs solar radiation, storing vast amounts of heat. This heat is released slowly, influencing air temperature and weather patterns. Warm ocean waters fuel hurricanes. The warmer the water, the more moisture evaporates. The more moisture, the more energy available. Hurricanes typically form when sea surface temperatures exceed 27 degrees Celsius. Ocean currents transport heat around the globe. The Gulf Stream warms Europe. The Kuroshio warms Japan. Without these currents, climates would be drastically different. The ocean also affects storms through evaporation. Water evaporates from the surface, adding moisture to the air. This moisture fuels rain and storms. Dry land cannot provide the same amount of moisture. The ocean's influence on storms is profound. It's both a source of energy and a moderating force. Coastal areas experience different weather than inland regions. Sea breezes cool coasts in summer. Storms weaken when they move over land, cut off from the ocean's heat and moisture. The ocean and atmosphere are deeply connected. They exchange heat, moisture, and energy continuously. The ocean's influence on storms is a reminder that Earth's systems are interconnected. The cycle of heat and water. Heat and water drive weather. The sun heats the surface. Water evaporates. Moist air rises. Clouds form. Rain falls. Water returns to the surface. The cycle repeats. This is the essence of weather. Heat and water, in constant motion. The cycle operates at all scales. Locally, a puddle evaporates, adding moisture to the air. Regionally, a thunderstorm releases rain over a county. Globally, tropical oceans evaporate vast quantities of water, which is carried by winds to distant lands. Without this cycle, weather would not exist. The planet would be static, but as long as the sun shines and water exists, the cycle continues. The cycle of heat and water is also the water cycle. Evaporation, condensation, precipitation. It's been operating for billions of years. It will continue as long as Earth has oceans and an atmosphere. The cycle is elegant, simple in principle, complex in detail. It connects the ocean, atmosphere, and land. It sustains life. Without it, Earth would be a barren desert. The cycle of heat and water is the heartbeat of the planet. It's constant, eternal, and it's the foundation of all weather. How evaporation drives the weather. Evaporation is the process by which liquid water becomes vapor. It requires energy, heat. The sun provides this energy. When water evaporates, it takes heat with it. This is why sweating cools you. The water on your skin evaporates, removing heat from your body. In the atmosphere, evaporation occurs constantly. Water evaporates from oceans, lakes, rivers, soil, and plants. This vapor rises into the air. As it rises, it carries heat, latent heat. When the vapor condenses back into liquid, the heat is released. This released heat warms the air, making it rise further. Storms are powered by this process. How evaporation drives the weather is fundamental. Without evaporation, there would be no clouds, no rain, no storms. The atmosphere would be dry and stable. Evaporation adds moisture and energy to the air. It's the starting point of the water cycle. It's the fuel for weather. Evaporation is invisible. You can't see water molecules leaving the surface, but the effects are everywhere. Clouds, rain, humidity, all begin with evaporation. How evaporation drives the weather is a story of energy transfer. Heat from the sun becomes motion in the atmosphere. Liquid becomes gas, and weather is born. The journey of a water molecule. Imagine a single water molecule. It starts in the ocean. The sun heats the surface. The molecule evaporates, becoming vapor. It rises into the atmosphere. Wind carries it across the sea. It joins billions of other molecules. Together, they form a cloud. The cloud drifts over land. The air cools. The molecule condenses onto a dust particle. It becomes part of a raindrop. The raindrop grows. Eventually, it falls. The molecule lands on a leaf in a forest. It slides down the leaf into the soil. A tree root absorbs it. It travels through the tree into a leaf. The leaf releases it through transpiration. The molecule evaporates again. It rises into the air. This time, it freezes into an ice crystal. It becomes part of a snowflake. The snowflake falls onto a mountain. It becomes part of a snowpack. In spring, it melts. The molecule flows into a stream. The stream joins a river. The river flows to the ocean. The molecule is back where it started. The journey of a water molecule is endless. It cycles through atmosphere, land, and ocean. It can take days or thousands of years to complete a cycle, but the journey never truly ends. Water is endlessly recycled. The molecule that falls as rain today might have been in a dinosaur millions of years ago. Water connects all of Earth's history. The endless water cycle. The water cycle has no beginning or end. It's a continuous process. Evaporation lifts water into the atmosphere. Condensation forms clouds. Precipitation returns water to the surface. Runoff carries water to oceans. And the cycle repeats. The cycle operates on multiple timescales. A puddle evaporates in hours. A river flows to the ocean in weeks. Groundwater can remain underground for thousands of years. Ice in glaciers can last millions of years. But eventually, all water returns to the cycle. The endless water cycle is essential for life. It distributes fresh water. It regulates temperature. It shapes landscapes. Rivers carve valleys. Glaciers grind mountains. Rain nourishes forests. The cycle also transports nutrients and sediments. It connects ecosystems. A raindrop that falls in the mountains might carry nutrients to the sea. The water cycle is powered by the sun. Without solar energy, water wouldn't evaporate. The cycle would stop. The planet would freeze. The endless water cycle is one of Earth's defining features. It's been operating for billions of years. It will continue for billions more. It's the planet's circulatory system, and it's the foundation of weather and climate. The power of air pressure. Air pressure is the weight of the atmosphere pressing down. At sea level, it's about 1,013 millibars, or 14.7 pounds per square inch. We don't feel it because the pressure inside our bodies balances it. Air pressure varies with altitude. The higher you go, the less air above you, so pressure decreases. It also varies with temperature and weather. Warm air is less dense, creating low pressure. Cold air is dense, creating high pressure. The power of air pressure lies in its influence on weather. Air flows from high pressure to low pressure. This flow is wind. The greater the pressure difference, the stronger the wind. Low pressure systems are associated with storms. Air converges toward the low, rises, and cools. Clouds form. Rain follows. High pressure systems bring clear skies. Air diverges from the high, sinks, and warms. Clouds evaporate. Weather clears. Barometers measure air pressure. A falling barometer signals an approaching storm. A rising barometer indicates clearing weather. The power of air pressure is subtle but profound. It governs wind, weather, and storm development. Pressure is invisible. You can't see it, but it's always there, shaping the atmosphere. And it's one of the most important factors in predicting weather. The rise and fall of weather fronts. A weather front is a boundary between two air masses with different temperatures. When warm and cold air meet, they don't mix easily. They form a front. There are several types of fronts. A cold front occurs when cold air pushes under warm air. The warm air is forced to rise rapidly. This creates towering clouds and often severe weather. Thunderstorms, heavy rain, strong winds. Cold fronts move quickly. A warm front occurs when warm air slides over cold air. The warm air rises gradually. This creates layered clouds and steady, prolonged rain. Warm fronts move slowly. A stationary front occurs when neither air mass is advancing. Weather can be unpredictable along stationary fronts. An occluded front occurs when a cold front overtakes a warm front. The warm air is lifted completely off the surface. Occlusions often bring complex weather. The rise and fall of weather fronts is a key part of mid-latitude weather. Fronts bring changes, shifts in temperature, wind, and precipitation. Watching for fronts is essential for forecasting. The passage of a front is often dramatic. Temperatures drop or rise sharply. Winds shift. Skies clear or cloud over. The rise and fall of weather fronts is the rhythm of weather in temperate regions. How warm and cold air collide. When warm and cold air meet, They don't blend smoothly. Warm air is less dense. Cold air is more dense. The cold air slides under the warm air like a wedge. The warm air is forced upward. This lifting creates weather. If the warm air is moist, clouds form. If the lifting is strong, storms develop. The collision of warm and cold air is most dramatic along fronts. Cold fronts push under warm air aggressively. The warm air rises rapidly. Thunderstorms erupt. Tornadoes can form. Warm fronts are gentler. The warm air glides over cold air gradually. Clouds form in layers. Rain falls steadily. But the principle is the same. When air masses with different temperatures collide, the lighter air rises. How warm and cold air collide determines much of our weather. In winter, Arctic air plunges south, colliding with warmer air. Snow and ice storms result. In summer, tropical air pushes north, colliding with cooler air. Thunderstorms and heavy rain follow. The collision is not just a local event. It's part of the global heat transport system. Warm air moves poleward. Cold air moves equatorward. They meet in mid-latitudes. The collision creates the ever-changing weather we experience. It's dynamic, restless, and endlessly fascinating. The patterns of global winds. Winds don't blow randomly. They follow patterns determined by Earth's rotation and uneven heating. At the equator, warm air rises, creating a zone of low pressure called the doldrums. The rising air moves toward the poles at high altitude. At about 30 degrees latitude, it sinks, creating high pressure zones. This sinking air flows back toward the equator at the surface. These are the trade winds. Between 30 and 60 degrees latitude, surface winds blow toward the poles. These are the westerlies. They're the prevailing winds in mid-latitudes. At the poles, cold air sinks and flows toward the equator at the surface. These are the polar easterlies. These wind patterns, trade winds, westerlies, polar easterlies, create the general circulation of the atmosphere, but local factors complicate the pattern. Mountains deflect winds, oceans moderate temperatures. The result is a complex tapestry of wind patterns. The patterns of global winds have shaped human history. Sailors used trade winds to cross oceans. Explorers followed westerlies. Understanding wind patterns was essential for navigation and trade. The patterns of global winds connect the planet. They distribute heat and moisture. They drive ocean currents. They shape climates, and they're the background against which all weather occurs. The trade winds and jet streams. The trade winds are steady winds that blow from east to west in the tropics. They were named by sailors who used them for trade routes. The trade winds are remarkably consistent. They blow almost every day, year-round. They're created by the Hadley cell circulation. At the equator, air rises. At 30 degrees latitude, it sinks. The return flow at the surface curves due to Earth's rotation, creating the easterly trade winds. Jet streams are different. They're narrow bands of fast-moving air at high altitudes. The polar jet flows between 30 and 60 degrees latitude. The subtropical jet flows near 30 degrees. Jet streams form at boundaries between warm and cold air. The temperature difference creates a pressure gradient. The wind accelerates. Jet streams meander, looping north and south. Their position influences weather. When the polar jet dips south, cold air follows. When it retreats north, warm air moves in. The trade winds and jet streams are both part of the global circulation, but they operate at different altitudes and for different reasons. Together, they transport heat and moisture around the planet. Understanding them is essential for weather forecasting. They're the rivers of the sky, carrying weather from one region to another. How mountains shape the weather. Mountains are barriers to airflow. When air encounters a mountain, it must rise. As it rises, it cools. If the air is moist, clouds form on the windward side, the side facing the wind. Rain or snow falls. This is called orographic precipitation. By the time the air crosses the peak and descends the other side, it has lost most of its moisture. The descending air warms and dries. This creates a rain shadow, a dry region on the leeward side of the mountain. Rain shadows create deserts. The Atacama Desert in Chile exists because of the Andes. The Gobi Desert exists because of the Himalayas. Mountains also channel winds. Valleys funnel air, creating local wind patterns. Mountain and valley breezes occur daily. During the day, slopes heat up. Air rises, creating upslope winds. At night, slopes cool. Air sinks, creating downslope winds. How mountains shape the weather is profound. They create microclimates. They influence precipitation patterns. They affect temperatures. A mountain range can divide a region into wet and dry zones. The windward side is lush and green. The leeward side is arid and brown. Mountains are sculptors of weather. They force the atmosphere to react to their presence.